Okay, get this. What if I told you that the faster you go, the slower you age? I know, it sounds like something straight out of a sci-fi movie, right? But it's actually a fundamental truth of our universe. And today, we're going to dive into this totally mind-bending idea, why the fastest clock is, believe it or not, also the slowest. It all comes down to something called time dilation. So let's just start with a really simple question, one we almost never bother to ask. Does time pass at the same rate for everyone? I mean, your gut reaction based on, your entire life is probably screaming, yeah, of course it does. But, well, as you're about to find out, the universe has a very, very different answer, and it gets pretty weird. All right, here's how we're going to tackle this. First, we'll poke some holes in the idea that time is constant. Then we'll get into Einstein's two simple rules that basically turned physics upside down. From there, we'll check out the light clock experiment, look at some real-world proof, and this is the cool part, see how relativity is sitting right there in your pocket. Okay, first up, time isn't constant. And yeah, this one's all about challenging what feels like common sense. We all kind of think of time like this big universal river, right? Just flowing along at the exact same speed for everybody, everywhere. But it turns out that's really just an illusion, one that's created because, well, we live pretty slow lives, cosmically speaking. And that right there is the key. The whole reason we don't notice time doing weird things is that the effect is, well, it's pretty much zero at the speeds we're used to, like driving a car or even flying in a jet. But the moment you start getting close to the ultimate speed limit, the speed of light, that tiny, tiny effect, it doesn't just get a little bigger. Oh no, it becomes absolutely dramatic. So how in the world did we even figure this out? Well, that brings us right to our second section, Einstein's two simple rules. The entire foundation for this complete overhaul of how we see time and space, it all rests on just two shockingly simple ideas from his theory of special relativity. And what's so wild is how simple these rules are. The first one, it makes total sense. The laws of physics work the same for everybody, as long as you're not accelerating. Easy enough. But that second rule, oh man, that is the game changer. It says the speed of light in a vacuum is always the same. It doesn't matter if you're standing still or flying towards the light source or away from it. You will always measure the same speed. And that one little fact, it breaks everything we think we know about the world. Now, for that second rule to actually be true, we have to completely change our perspective. We have to stop thinking about space and time as two different things. They're not. They're actually woven together into this single four-dimensional fabric called space-time. And this leads to a fundamental trade-off. Think of it this way. The faster you move through space, the slower you have to move through time. Okay, I get it. That's still a little abstract, right? So let's make it real. Let's move on to our third section, the light clock experiment. This is honestly just a brilliant thought experiment that shows you, without any crazy math, why time absolutely has to slow down for anything that's moving. So just imagine the simplest clock you can. It's basically two mirrors, and we've got a little particle of light, a photon, just bouncing between them. Every time it makes a full trip, up and down, that's one tick of the clock. Simple. Now, for this to work, we need two different points of view. We've got observer 1, who's riding right alongside the clock, and we've got observer 2, who's just standing still, watching this whole thing fly by. Okay, so for observer 1, the person who's actually on the clock, everything is totally normal. From their perspective, nothing's moving. The little photon just goes straight up, bounces off the top mirror, and comes straight back down. Tick, tock. A nice, short, simple path. But now, what does observer 2 see? From where they're standing, the clock is whizzing by. So for that photon to get from the bottom mirror to the top one, it's not just going up anymore. It also has to travel forward to keep up with the moving clock. It has to travel along a longer, diagonal path. And it's the same thing on the way back down. And this is the big aha moment. Remember that unbreakable rule from Einstein? The speed of light has to be the exact same for both observers. So, let's think about this. If the light for observer 2 has to travel a longer distance, but it's moving at the exact same speed, then it just has to take more time to make the trip. It's the only way it works. So from the outside looking in, that moving clock is literally ticking slower. So yeah, there's an equation for this, the Lorentz transformation. But look, don't get hung up on the math. Just look at the relationship. You see the v for velocity and the c for the speed of light? The closer v gets to c, the bigger that final time measurement gets. It's really that simple. The faster you go, the more time slows down for you compared to everyone else. And this chart really shows you just how crazy it gets. Look at this. At half the speed of light, time is already slowing down by about 15%. But jump up to 90% of light speed, and time is now moving more than twice as slow for you. And at 99.9%, your clock would be ticking over 22 times slower than a clock back on Earth. This isn't just a straight line. The effect grows exponentially. All right, so a thought experiment with a light clock is cool and all, but is any of this stuff, real? And the answer is a resounding yes, absolutely. Which brings us to section 4, proof in the real world. This isn't just some abstract theory anymore. It is one of the most proven, most tested facts in all of physics. And we see the proof all over the place. For example, there are these tiny particles called muons that are created way up in our atmosphere. They should decay long before they reach the ground. But they travel so fast, their internal clocks literally slow down, letting them survive the trip. We've also done the obvious experiment. We put super precise atomic clocks on jets, flew them around the world, and guess what? They came back running just a little bit slower than the clocks we left on the ground, by the exact amount Einstein's math said they would. And particle accelerators? They wouldn't even work if the engineers didn't account for this. Okay, so this still might feel like something that only matters to physicists in a lab or astronauts in deep space. But it's not, I promise you. Which brings us to our last section, relativity in your pocket. Because this cosmic rule matters to you probably every single day. Just think about the GPS on your phone. You probably use it all the time, right? Well, it works by talking to a whole network of satellites that are orbiting the Earth. And those satellites are moving fast. We're talking thousands and thousands of kilometers an hour. That's definitely fast enough for time dilation to stop being a theory and start being a real, measurable problem. See, because those satellite clocks are moving so fast compared to us down here, their clocks tick just a fraction of a second slower every day. Doesn't sound like much, does it? But if the engineers who built the GPS system didn't constantly correct for this effect, the errors would add up. Your location would be off by about 10 kilometers. That's over 6 miles every single day. After just one day, your GPS would be totally and completely useless. So where does all this leave us? Well, it leads to one last, pretty mind-blowing question. If an astronaut takes a journey traveling near the speed of light, we know their clock will tick much, much slower. So, if that journey felt like just a few years to them, is it actually possible that when they finally came back home, decades or maybe even centuries could have passed for everyone they left behind on Earth? And the answer, according to everything we know about physics, is yes. Time, it turns out, is anything but simple. It's truly and wonderfully relative.